The title of this paper is Towards Optimal Set-Disjointness and Set-Intersection Data Structures. My name is Tsvi Kopelowitz, and this is joint work with Virginia Vassilevska-Williams from MIT. We begin by defining the set-disjointness problem. In the set-disjointness problem, the goal is to preprocess a family of k sets, all from some universe, so that given a query ij, we can quickly determine whether Si and Sj are disjoint or not. The efficiency of our algorithms are going to be measured in terms of capital N, which is the sum of the sizes of the sets. So in the example here, k equals 4 since we have 4 sets, and capital N equals 9 since the sum of the sizes of the 4 sets is exactly 9. If, for example, we're given 1 and 4 as input, we can see that the sets S1 and S4 both contain the white element, so the answer is that the two sets are not disjoint. But if the input is 2 and 3, then we can see that S2 and S3 do not share any elements, so the answer is that they are disjoint. There are two trivial algorithms that I would like to show first. The first algorithm is based on lookup tables. In the preprocessing phase, the algorithm stores each set in its own lookup table that allows for constant time lookups. The preprocessing costs linear time. Given a query, the algorithm considers each element in the smaller of the two sets and checks whether the element is also in the larger set using the lookup table. If the answer is always no, then the two sets are disjoint. And if the answer is yes at least once, then there is at least one shared element, and so the two sets are not disjoint. The query time in this case is linear in the size of the smaller set, which is at most linear in n. The second algorithm is to construct an oracle by pre-computing the answers for all possible pairs of sets. The preprocessing time could be as large as order of n squared, which happens when all of the sets have constant size. The query is clearly answered in constant time by looking up the pre-computed answer. If we denote the preprocessing time by n to the p and the query time by n to the q, the table to the right here shows that the two trade-offs that we just saw have these values here of p and q. So for the tables algorithm, we have p equals 1 and q equals 1, and for the oracle algorithm, we have p equals 2 and q equals 0. Notice that in both cases, p plus q equals 2, and so a natural question to ask is whether there is a trade-off between the two extremes. The answer to this question is yes, and we will now show such a trade-off. This trade-off algorithm is somewhat folklore, but the first time we found this idea mentioned is in a paper by Chagai Cohen and Eli Porat from 2010. The algorithm is based on a heavy-light partitioning. We say that a set S is heavy if the number of elements in S is at least n to the alpha for some parameter alpha that is between 0 and 1. Since the total number of elements in all of the sets is n, we cannot have more than n to the 1 minus alpha heavy sets. For the preprocessing phase, we apply the preprocessing of the table data structure, which costs linear time, and we also apply the preprocessing of the oracle algorithm, but this time only for pairs of heavy sets. By restricting ourselves to pairs of heavy sets, the preprocessing time becomes order of n to the 2 minus alpha. For the query algorithm, if the two sets are heavy, then we apply the oracle query algorithm since we have pre-stored the answer. If at least one of the sets is light, then we apply the table query algorithm by scanning all of the elements in the light set and using the lookup table of the other set. Since each light set has at most n to the alpha elements, the total query time is at order of n to the alpha. So now if we update our table here to the right, the trade-off algorithm has p equals 2 minus alpha and q equals alpha for any choice of alpha between 0 and 1. And so the trade-off curve is the line of p plus q equals 2. When comparing different algorithms for set disjointness, we would like to restrict our attention to values of p and q that are meaningful. For example, if we make the standard assumption that any preprocessing algorithm should scan the input at least once, the preprocessing time must be at least linear in n, and this means that p is at least 1. On the other hand, for p equals 2, the oracle algorithm that we showed before provides a constant query time, so there is no point in considering values of p that are larger than 2. For the query time, a trivial query algorithm costs linear time, and so there is no point in concerning values of q that are larger than 1. So we're going to restrict ourselves to this two-dimensional graph with values of p between 1 and 2, and values of q between 0 and 1. The trade-off algorithm that was based on a heavy light decomposition gives the following curve. And so we know that the true optimal curve of the set-disjointness data structure problem is at or below this particular curve. The best known conditional lower bound is from a joint paper with Seth Petty and Eli Porat, where we showed that based on the three-sum hypothesis, we have p plus 2q is at least 2. This is a good place to point out that many of the known conditional lower bounds that are based on the three-sum hypothesis use set-disjointness as an intermediate problem in their reduction. And in particular, these lower bounds depend on this particular curve. This is also a good place to point out that based on the combinatorial Boolean matrix multiplication hypothesis, the heavy light trade-off algorithm is optimal for combinatorial algorithms. However, for non-combinatorial algorithms, the lower bound and upper bound curves that we can see over here leave a large gap between them. And so in this paper, we address the question of whether or not we can close this gap. Our first step is to show an improved algorithm for the set-disjointness problem with a better upper bound curve. Since we want to break the combinatorial Boolean matrix multiplication hypothesis, we're going to have to use non-combinatorial techniques, and in particular, we're going to use fast matrix multiplication. The algorithm is based on the previous heavy light trade-off algorithm, but we're going to design a faster method for precomputing the oracle on the heavy pairs. To do so, we represent the heavy sets using a sparse Boolean matrix as shown in this example. So over here, we're going to assume that each one of the four sets is a heavy set. Each row in this matrix corresponds to a particular set, and each column corresponds to an element from the universe. The rows are just the characteristic vectors of the appropriate sets. Our goal is to compute the Boolean product of this matrix with its transposition. To see why, consider the ith row of the matrix and the jth column of its transposition. These two vectors correspond to the characteristic vectors of the sets Si and Sj, and so their Boolean inner product is 0 if and only if the two sets are disjoint. This outcome is stored in the ij location of the output matrix. In order to compute this Boolean matrix product, we want to take advantage of the matrix being sparse, and this is true since the number of ones is at most n. N is in general much smaller than the size of the matrix, so our matrix is indeed sparse. Our algorithm is essentially the sparse matrix multiplication algorithm of Euster and Tsvi. One subtlety here, for efficiency purposes, is that the matrices are represented using sparse representations. So this is happening in the background, but I will be ignoring the subtlety going forward. We define the frequency of an element E to be the number of sets that contain E, and denote this number by Fe. Notice that Fe is exactly the number of ones in the column corresponding to E. We say that E is rare if Fe is at most n to the beta for some parameter beta between 0 and 1. Otherwise, we say that E is frequent. Notice that, as before, the number of frequent elements is at most n to the 1 minus beta. Our algorithm has two parts, one for rare elements and one for frequent elements. In the first part, the algorithm extracts information from rare elements using an outer product. One outer product for each rare element. The outer product for each rare element is between the column in the first matrix corresponding to the rare element and the corresponding row in the transposed matrix. In order to compute this outer product efficiently, the algorithm enumerates all pairs of sets that both contain E. Since E is contained in Fe sets, the time cost for each inner product is Fe squared, and so the total time cost of all outer products is at most order of n to the 1 plus beta. You can do the math if you want to verify. For the frequent elements, the algorithm uses fast rectangular matrix multiplication. This is the non-combinatorial aspect of our algorithm. Notice that the size of the matrix now is n to the 1 minus alpha times n to the 1 minus beta, since there are at most n to the 1 minus alpha heavy sets and at most n to the 1 minus beta frequent elements. Finally, the algorithm merges all of the information from all of the outer products and the information from the frequent elements into one matrix. The total preprocessing time is n to the 1 plus beta for the rare elements, and the time for computing fast rectangular matrix multiplication for the frequent elements. The query time is the same as in the heavy light trade-off algorithm, which is still n to the alpha. In order to simplify the presentation here, suppose that omega, which is the exponent in the optimal time cost of multiplying two n by n matrices, is 2. With this assumption, we have the following two-piece curve. For q less than a third, we have p plus 2q equals 2, and for q at least a third, we have 2p plus q equals 3. Intuitively, the reason the curve has two pieces has to do with the way in which the time cost of fast rectangular matrix multiplication algorithms depend on the dimensions of the matrices. So now we can see that the new algorithm reduces the gap that we showed before. And in particular, for small values of q and large values of p, we obtain an optimal algorithm conditioned on the three-sum hypothesis. This is for values of q which are less than 0.13156 and values of p which are larger than 1.73688. If we assume that omega equals 2, the algorithm is optimal for q between 0 and a third, but for q between third and 1, we still have a gap. Now, in order to close this gap, we're going to turn to conditional lower bounds. And in particular, our conditional lower bound is based on a new hypothesis, which I will now try to motivate. Our new hypothesis is closely related to the triangle detection hypothesis. In the triangle detection problem, the input is an undirected graph G with m edges, and the goal is to decide whether G contains a triangle or not. Alon Yuster and Tsvi designed an algorithm whose runtime is order of m to the 2 omega over omega plus 1, which for omega equals 2 is exactly m to the 4 thirds. One of the popular hypotheses in the world of conditional lower bounds is that any algorithm for triangle detection must cost at least omega of m to the 4 thirds time. It turns out that the problem of triangle detection is still hard even when the graph is tripartite. To see this, suppose we convert the original graph into a tripartite graph as follows. We begin by creating 3 copies of the vertices. So in this example here, each vertex, for example, vertex I, has 3 copies, 1 in each one of the sets. We then create 6 copies of each edge. So for example, the edge ij has 6 copies here. Notice that this graph is tripartite since we do not add edges between vertices in the same set. So a triangle in the original graph becomes a bunch of triangles in the tripartite graph. Also, it is not too hard to see that the reverse is true as well, since a triangle in the tripartite graph must correspond to a triangle in the original graph. This means that the triangle detection problem in tripartite graphs is equivalent to the triangle detection problem in general graphs. Notice that the edges between any 2 sets of the tripartite partition correspond exactly to the edges from the original graph. So between every 2 sets of the partition, there are exactly m edges. We say that such a tripartite graph is balanced. A natural question to ask is whether we can design better algorithms for the case of the tripartite graph being unbalanced. This leads us to the problem of unbalanced triangle detection, where the input is a tripartite graph where the number of edges between different sets that define the partition of the graph can be different. In particular, if m1 is the number of edges between A and B, m2 is the number of edges between B and C, and m3 is the number of edges between C and A, then we assume without loss of generality that m1 is at most m2, which is at most m3. The goal is still to establish whether this graph contains a triangle or not. By adapting techniques used for general graphs, we design a new algorithm whose runtime is expressed here. And for simplicity, if we assume that omega equals 2, like we did before, then the runtime becomes m3 plus m1 times m2 to the third times m3 to the 2 thirds. Our new hypothesis states that this is the best that one can obtain for unbalanced triangle detection. One possible motivation for believing the unbalanced triangle detection hypothesis is that this hypothesis implies the standard triangle detection hypothesis. To see this, just set M1 to be the same as M2 and the same as M3. If we believe the unbalanced triangle detection hypothesis, then the following reduction from unbalanced triangle detection to set disjointness closes the remaining gap. The reduction works as follows. We first set the vertices in C to be the universe, and for each vertex in A or B, we create a set that contains all of the neighbors from C. So for example, the set of lowercase a is the set of neighbors of A, which are the three colors over here, and the set for lowercase b is defined in a similar way. The rest of the reduction is based on a straightforward observation that the graph contains a triangle if and only if there exists a set from A and a set from B that are not disjoint. So, the reduction algorithm preprocesses the sets defined by A and B into a set disjointness data structure. And for each edge between A and B, the reduction algorithm performs one set disjointness query. Notice that the size of the set disjointness instance is the number of edges in the cut between C on one side and A and B on the other side. Since M3 is the largest number of edges, we have that N is order of M3. The queries correspond to the edges between A and B, and so the number of queries is exactly M1. Finally, the time to solve unbalanced triangle detection becomes N to the P plus M1 times N to the Q, since we preprocess the set disjointness instance exactly once and perform M1 queries. By plugging in the value of N, as we saw before, and applying the unbalanced triangle detection hypothesis, we obtain this conditional lower bound curve, which behaves differently depending on the relationship between M1, M2, and M3. We are now ready to show how this curve looks in our two-dimensional graph. So here we have both of the curves from the two pieces of the conditional lower bound we just saw. And since we are considering a lower bound, the upper envelope of the two lines gives us a conditional lower bound curve. This curve matches the threesome lower bound curve for Q less than a third, and it also matches the upper bound curve obtained by our new algorithm, assuming that omega equals 2. So we conclude that if we believe the unbalanced triangle detection hypothesis, and we believe that omega equals 2, then our algorithm is polynomially optimal. And even if we don't believe the unbalanced triangle detection hypothesis, but we believe the threesome hypothesis, then our algorithm is optimal for small values of Q. For the last few minutes, I want to briefly mention the set intersection problem. This is a version of set disjointness where the goal isn't just to decide whether or not the two sets are disjoint, but rather we are interested in enumerating all of the elements in the intersection. We will only consider algorithms whose query time is n to the q plus something linear in the size of the output. When applying the heavy light algorithm that we saw at the beginning of the talk on the set intersection problem, we obtain the same upper bound curve of p plus q equals 2. Based on the threesome hypothesis, it is known that this curve is tight for q which is less than 2/3. But for q greater than 2/3, a gap still remains. We close this gap by introducing an unbalanced triangle enumeration hypothesis, which is similar to the unbalanced triangle detection hypothesis, but now the goal is to enumerate all of the triangles in the unbalanced tripartite graph. Using a similar thought process as in the unbalanced triangle detection hypothesis, and a reduction from unbalanced triangle enumeration to set intersection, we show that the upper bound curve is conditionally optimal for all values of p and q. So to summarize, we introduced new algorithms for set disjointness, unbalanced triangle detection, and unbalanced triangle enumeration. We also introduced the unbalanced triangle detection hypothesis, and if we believe this hypothesis and assume that omega equals 2, then our new set disjointness algorithm is optimal. We also introduced the unbalanced triangle enumeration hypothesis and showed that the heavy-light trade-off algorithm is optimal for set intersection if we believe the unbalanced triangle enumeration hypothesis. Finally, as an open problem, we leave the question of what can we do for problems that are threesome hard, and the proof that they're threesome hard goes through the set-disjointness problem. As we mentioned earlier, this happens for many of the problems that are known to be threesome hard. The question is whether or not we can design faster algorithms for such problems that take advantage of fast matrix multiplication or fast rectangular matrix multiplication. Thank you very much for listening.